This is tutorial 7, problem 13.40. The problem goes as follows. Water flows through a venturimeter that has a 40 centimeter throat. The venturimeter is in a 70 centimeter pipe. What deflection will occur on the mercury water manometer connected between the upstream and throat sections if the discharge is 0.75 cubic meters per second? Assume the temperature of water is 20 degrees C. So I have drawn an illustration of what the problem will look like. There's a venturi, the water is flowing from left to right. The throat is 400 millimeters or 40 centimeters. The pipe diameter is 700 millimeters or 70 centimeters. We're also given the discharge of 0.75 cubic meters per second. We're told that water is 20 degrees C. So we can look up the kinematic viscosity, 1 times 10 to the minus 6 meters squared per second. You can see the mercury manometer connected, and we're asked to calculate what is that deflection. All right, so we start off with the Reynolds number. So to calculate the Reynolds number, we use the formula that you find on page 49. 4 Reynolds numbers in this application, which is 4Q, Q being the discharge, over pi d and mu. All right, substituting into that formula, we get 4 times 0.75, which is the discharge, divided by pi, times the diameter is 0.4. That is the throat diameter. And then mu we know is 1 times 10 to the minus 6. Now that will give us an answer for the Reynolds number of 2.39 times 10 to the 6, which is turbulent. And we know that because it is above 3,000. All right, now we have to determine the flow coefficient on figure 13.15 as we've done before. And we need a few things to do that, to read that off the graph. So we need the value of d over d. So that's 400 over 700. So that's the ratio of the throat to the inlet, and that gives us 0.571. And then using figure 13.15 gives us a K value of 1.05 flow coefficient. All right. The next thing we're going to do is calculate using the Venturi equation. And that is written Q is equal to K AT square root 2G delta H. So that is, this charge is equal to flow coefficient times the area of the throat times the square root of 2G delta H, which is your head differential. So if we have to make delta H the subject of the formula, in other words, what is the head difference in pressure between the pipe and the throat? So let's take delta H to the front of the formula. That becomes Q over KAT squared. We divide that all by 2 G. Delta H substituting into the formula, we've got 0.75. K, we know is 1.05. And then area is pi over 4 times 0.4 squared. We square that whole term, divide that all by 2 times 9.81. Delta H therefore equals 1.65 meters of water. So now we have the head difference between the throat and the pipe. So this is what's causing the deflection in the mercury manometer. So using the manometer equation, we can now analyze the mercury manometer. So there's our manometer formula. So we're converting due to the densities. What would the difference in height of a column of mercury be due to that head difference of water? So if we substitute delta H, we've just calculated as 1.65 meters of water, and then we substitute for the densities. We've got 13.55 minus 1, and we get the head of, the height difference of mercury would be equal to 0.13 meters. And that is what we were asked to calculate.